Okay, this is team 3. We're going to explain our proposal about term projects. Next. And this is this we will introduce. In recent years, deep reinforcement learning has enabled impressive capabilities in robotics, such as learning complication manipulation and learning to adaptation in unstructured environments. Despite this advance, reinforcement learning faces a struggle in running long horizon manipulation tasks. They usually fall short in long horizon tasks due to the explanation burden. According to this paper, they use simple idea that the long horizon task can be decomposed by elementary orders motor actions. The authors describes that this task can be solved through multiple primitives and selection properties. And now we introduce a new deep reinforcement learning framework called MAPLE, which is figured out in ICRA 2022, and explain our improvement plan. In reinforcement learning, the model considered the problem of the computational agent learning to make decisions by trials and error. Deep reinforcement incorporates deep learning into the solution, allowing agents to make decisions from unstructured input data without manual engineering of the state space. But the limitation has been figured out when it solved the complex and long sequential task. For solving this problem, recent work has harnessed pre-built primitives. However, these work are limited as they are confined to use only one or two specific primitives or employ rigid primitives that are not reconfigurable, or the hardcore how the primitives are composed. In contrast, MAPLE method adapts a set of versatile primitives to solve diverse manipulation tasks. The formulation specifically for under the established reinforcement learning framework of a parameterized action MTP is called PAMTP. PAMTP is method that the agent executes a parameterized primitive at each decision-making step. They develop manipulation primitive augmented reinforcement learning, simply MAPLE, based on the insight obtained from these prior studies. Tae-yoon will explain in more detail.
First, I will explain the basic notion, the primitives. The manipulation tasks such as lifting and stacking objects have high dimensional action spaces or search spaces. So aforementioned in the intro chapter, it takes a lot of time to solve this kind of problem with RL. Thus, in this paper, they try to augment such tasks to a behavior primitives. In other words, they divide tasks to sub-level tasks, smaller and simpler. Again, augmenting action space with a heterogeneous library of behavioral primitives. At each decision-making step, the agent executes a parameterized action such as reaching, grasping, pushing, grip release, and atomic. Here is a page with the explanation of 5 primitives. In their framework, they follow the PAMTP framework. However, it has a major drawback. When the additional primitives are introduced, the total number of policy outputs quickly become intractable. So to address this issue, the hierarchical policy is used with a high-level task policy and the low-level parameter policy. The learning model looks like this figure. The task policy is a single neural network and the parameter policy is a collection of sub-networks, which is a green. The one sub-network dedicated for each primitive. With this framework, each primitive can have own heterogeneous parameters. With observation, the task policy network chooses one primitive type A with softmax function. Then, with chosen primitive type A, it chooses a dedicated subnetwork in collection of primitive parameter sub-policy network. The network outputs primitive parameters. To train this model, the soft actor critic, which is the algorithm to find solutions to entropy maximization problems using neural network. It maximizes 3 Q values: critic, actor, and hierarchical policy. The primitives change the task problem to the temporal abstraction. The trained model can take less time to explore the searching space. However, this feature can present on exploration challenges, which makes interactable and time-consuming. So they equipped the agent with affordances. In this framework, affordances can be expressed by adding the reward function on auxiliary affordance score that measures the affinity of parameter x at a particular stage s for a given primitive type A. To 8 tasks and 4 baselines to their method, they compared how the reward is changed as the training goes on. The result shows Maple achieved the highest average success rate across all baselines. And the efforts opened here are our replication plan. The efforts opened the original code in GitHub. So we replicate it and reproduce exactly what they did. We will use a pre-trained model in Visual environment. We will analyze this architecture structure for better improvement.
Okay. We focus on what we try to improve in this paper. First, naturally, if the higher-level task cannot be divided with basic primitive, the network interprets them all to atomic primitive, which is not defined well. Especially, this figure shows that the network repeats the atomic primitive until the peg is inserted when the model performs the peg insertion task. Second, the affordance is not enough to operate in complicated tasks, so some observation did not project proper action well. However, as in ablation studies figure, if there is no affordance, the network cannot finish the task at all. Therefore, the model relies on affordance, but affordance cannot predict the proper primitive, which results in worse. In conclusion, what we will concentrate is how primitive selection performs better. We will improve the idea in depth in terms of them. First is primitive. We will regulate the model to be less dependent with atomic primitives. Second, about affordance, we will change the way of affordance prediction to data-driven method. Our main idea is extending type of a primitive to reduce ambiguity when primitive selection. To improve the model in terms of the primitive selection, first is adding more primitive type. We will express primitive in smaller unit, which is based on the simple movement, such as trajectory control, gripper control, rotation control, and anything else. After this, we will redefine current primitive to these smaller units. For example, a current primitive grasping is divided with reaching, rotating, and gripper closing. We will express primitive in smaller unit. To utilize the data-driven affordance network, we choose 2 baseline network. We will use this model backbone. We will bring the model with the trained checkpoint. We will fine-tune the model with musical simulation image captured from the manipulator side. We will fix network except primitive police for fine-tuning, and we'll start retraining for adjusting new heads. Yeah, this is our presentation. Thank you for listening.